This is the AB 65 and 77 review, number 10, the free response with the calculator allowed. So we're given a chart of data that talks about the rate at which Mr. Rich drinks Dr. Pepper, and it's measured in ounces per hour given by a differentiable function P. So part A, we want to use a midpoint Riemann sum with 6 subdivisions of equal length to approximate that accumulation. And then use correct units, we want to explain the meaning. So we want to accumulate from 0 to 6, and we want to use midpoints with 6 subdivisions. So it looks like we're going to do 1, 2, 3, 4, 5, 6. So the midpoints are going to come from these middle ones. So the width of each subinterval is 1, and then the height comes from the output, which is 9.5 and 10 and 10.9 and 6.3, 4.4, and 2. Add that all up and it looks like we get a 43.1. Now, using correct units, we want to explain the meaning. So let's think about what we just did. We had this P of T, which was measured in ounces per hour, and we were accumulating under it. And the inputs were measured in time or hours. So we essentially had time units times ounces per hour units, which meant the hours will cancel and we'll get ounces. So what this means is that Mr. Rich drank approximately 43.1 ounces of Dr. Pepper in the time interval 0 to 6 hours. Part B. Is there some time on the open interval such that the derivative of P equals 0? Okay, so this sounds like the conclusion of a theorem because I'm on an open interval and I've got a derivative. So I can either use Rolle's because I have a derivative that equals 0, or I can use the mean value theorem and just look for a secant slope that equals 0. So I'm going to use the mean value theorem, and I can say, okay, I will get a secant slope that's 0 if I have an output that is the same sometime between 0 and 6. So if I look at my outputs and trace through them, I see that I've got a 9.7 that shows up twice. That means if I do the secant slope between 1 and 3, I'm going to get a tangent slope somewhere in between that is a 9.7. And the reason I know that is because P is differentiable. So we can say yes, since P excuse me, is continuous and differentiable, on that whole interval from 0 to 6, or you could say from 1 to 3, because that was where we actually had the outputs that were the same. P prime of T must equal P of 3 minus P of 1 over 3 minus 1, which is the same as 9.7 minus 9.7 over 3 minus 1, which is 0. And actually, let me put a C here, for at least 1 C in the open interval from 1 to 3. And I guess we could say by the MVT. We might want to refer to the theorem. Okay, last part, C, says the rate at which Mr. Rich drinks Dr. Pepper can be modeled by this equation. So we can actually fit a curve to that, and they gave it to us. We want to use Q of T to approximate the average rate of Dr. Pepper consumption during the 6-hour period. So this is already the rate, and we want the average rate. So that means I'm going to do 1 over b minus a times the integral from a to b of that rate, which is q of t. So let's do that on our calculator. We'll do 1 divided by 6 times the integral of negative 0.431 t squared plus 1.379 t plus 8.72 with respect to t from 0 to 6. Diamond enter. We get 7.685 even. And how will we measure that? Well, let's think about what this is representing. This is time, so this is hours on the bottom. And when we accumulate that rate, we would get the number of ounces. That's what we figured out in part A. So we'll have an ounce on top and an hour on the bottom, so it's ounces per hour. So use Q of T to approximate the average rate. It makes sense that the average rate should be a rate of Dr. Pepper consumption. So we're finished.